Today we're going to look at some gas laws and how to apply those gas laws to some problems. It's going to be really handy if you have your STAAR chart nearby, because your STAAR chart has several of these laws, also gas constants. It'll also have conversions from Celsius to Kelvin. So get that STAAR chart ready, and we're going to whip through a few of these. We'll skip a few. The key thing to remember is look at your units and look at the information that's given in the problem. Circle it as best as you can or underline it so you can keep track of what you have. Here we have a volume, we have a pressure, and we have another pressure. If you have pressures and volumes, you're going to use something called Boyle's law, which says that P1 V1 is equal to P2 V2. So if you plug in V1, P1, and P2 and you're solving for V2, you will get a volume of 2 liters. Now be careful, because you want to look at your units. This has kilopascals, this has kilopascals, so they end up canceling each other out and you get volume in units. You can only have 1 sig fig here because this only gave you 1 sig fig. If you look at this one, it gives you a volume in milliliters. This other one is volume in milliliters. The milliliters will cancel. Usually you have to convert them to liters, but in this case they cancel. Uh-oh, watch out for your temperature. All temperatures must be in Kelvin when working with gas. So this is not in Kelvin. In order to get Kelvin, you take your degrees centigrade or Celsius plus 273, and you'll get whatever your temperature is in Kelvin. So in this case, we're going to take negative 55, add 273, and we're going to get 218 Kelvin. That's the temperature we have to use. So this is our first temperature, this is our first volume, and it asks for the new temperature. When you look on your STAAR chart, you'll see that when you're looking at temperatures and volumes, you're going to use an equation that looks like this. Okay, so if you put 550 for V1, 760 for V2, and you're going to put 218 in for T1, and then when you're solving for T2, be careful for your algebra. You're going to get 301 degrees, or not degrees, it's Kelvin. This one has some extraneous information. It's just there to distract you. There's nothing that talks about feet in any of these gas laws. You're going to find this inches of mercury here. This is a pressure. Then you're going to get a temperature. Now be careful, because this temperature is going to have to be 23 plus 273 to make it in Kelvin. So T1 is going to be 296. T2 is right here. So T2 is equal to 9 plus 273. So T2 is equal to 282 Kelvin, because again we want to work on Kelvin. So you've got one pressure, 2 temperatures, and it asked for a new pressure. So what's the P2? So when you look on your STAAR chart, you will see that there's a formula, P1 over V1. Excuse me, P1 over T1 is equal to P2 over T2. These 1s and 2s stand for initial condition and final condition. So it doesn't really matter. The 1s and 2s are just there to represent that you start with this is your first condition, and you end with this is your second condition. So if you plug this information in, it asks for pressure. Since it gave you pressure in inches of mercury, you can certainly give it back pressure in inches of mercury, and when you do that, you can get 28 inches of mercury as the final pressure. Now be careful here, because you can only have 2 sig figs, because this 9 degrees only gave you 2 sig figs. You're going to use something called the combined gas law, and it looks like this. Okay, so let's double check our units that they match. This volume has liters, this volume has liters, so they'll cancel. This temperature has Kelvin, this temperature has Kelvin, so they'll cancel. So your pressure is going to be in kilopascals. So when you put everything in the formula, be careful for your algebra, you'll get a new pressure of 130, oops, My eraser doesn't want to work. Okay, you're going to get a pressure of 130 kilopascals as your new pressure. You can only have two significant digits or two significant figures because of your volume up here. Now down here, this is kind of interesting. It asks for gas. What gas can be produced from 2 liters of oxygen? Now, what's interesting about gases is that mole ratios equal liter ratios for all gases at standard temperature and pressure. So that's kind of helpful. This is not a gas, it's a solid. But if you look at these two other gases, 1 liter of oxygen will produce 2 liters of carbon monoxide, just like 1 mole of oxygen will produce 2 moles of carbon monoxide. Mole ratios, liter ratios, they're the same whenever you have these gases at STP, standard temperature and pressure. So if you have 2 liters of oxygen instead of 1 liter, you're going to produce double the amount or number of liters. So you'll produce 4 liters of carbon monoxide because your mole ratio is the same as liter ratios for gases at standard temperature and pressure. All right, we're going to keep going here. Okay, this is using the ideal gas law up here. You've got number of moles, you've got a pressure, you've got a volume. Uh-oh, look at this volume. This volume is going to have to be changed. You're going to need to convert 3,500 milliliters, and there's 1,000 milliliters in a liter, because your gas constant has liters. This also has to be in liters. Your pressure has to be in atmospheres, so here it is. This mole to the -1 and Kelvin to the -1 is the same as saying divided by moles and divided by Kelvin, so you can think of it as a fraction this way. You've got moles up here, so you're going to get temperature in Kelvin. Luckily, they ask you for temperature in Kelvin. So when you look at your ideal gas law, you're going to plug in P and V and number of moles and this gas constant, and you will get a temperature of 360 degrees. Excuse me, 360 Kelvin, it's not degrees. And you can only have 2 sig figs in this answer. You're limited by your volume. Okay, let's look at this one. This is a volume, but it's in milliliters, so be careful. This is a temperature in degrees Celsius, which is also not the right units. You've got a pressure here. Okay, so these are all your initial conditions, and they want to know what's the new volume if you have standard temperature and pressure. Standard temperature, well, let's come over here. All right, so our old volume is 180 milliliters. It says, I guess you can use volume for milliliters, so we can keep that to keep from having to do any more. Our temperature is 35 plus 273 to give us the right units for temperature, which is 308 Kelvin. Our pressure is 95.9 kilopascals. So if you look, our new volume is going to also be in milliliters. Our new temperature, or the final temperature, is standard temperature. Standard temperature is 273 Kelvin. That's on your star chart. Your standard pressure on your star chart is 1 atmosphere, but we don't have atmospheres. It's also 101.325, 325 kilopascals, which you don't even need all this stuff anyway. You just need the 101. So our kilopascals will cancel, our Kelvin will cancel, and so we'll get a volume that's in milliliters. So we're going to use the combined gas law. Okay, we're going to get a volume of 150 milliliters. All right, let's look at the next one. Number 8. A cylinder with a movable piston has a pressure of this amount. So we have a pressure and a volume in milliliters, so be careful with that. Uh-oh, this volume has liters, so we're definitely going to have to convert this other one to liters. and a temperature, which we'll have to also convert. So we have a pressure, initial pressure, an initial volume. We've got a final volume, and the temperature does not change. Uh-oh, what does this mean? Do we care about temperature then? If it doesn't change, you don't need to worry about it in the formula. So we're going to use P1V1 is equal to P2V2, which is Boyle's law because it's at constant temperature. So our pressure is atmospheres, and we want to know a new pressure, so we'll get atmosphere. We need to convert one of these volumes to match the other one. So I would convert the 400 milliliters to liters because typically volume is in liters. Okay. When you plug all those in, you get a new pressure of 1.07 atmospheres. Okay, let's look at this one. 2 liters, which is a volume, at 27 degrees. Now we want this to be 27 plus 273 is 300 Kelvin. That's what we would use. This is volume in liters, so that's V2. This is a pressure, P1, and we're converting it to 800 torr. Torr sounds kind of weird, but look, there's a handy chart here for 800 torr, which is a pressure. Torr is the same thing as millimeters of mercury, by the way. If you'll notice, those are the same numbers. Okay, so 800 torr, you have 760 torr for every 1 atmosphere. Since the first one's in atmospheres, we want the second one to be in atmospheres. And so when we convert that, we get 1.05 atmospheres. So now we have P2, P1, they're in the same units. We've got volume 1 and volume 2, they're in the same units. Our temperature up here is 300 Kelvin. So our new temperature will also be in Kelvin. And we're going to use the formula P1V1 over and P2V2 over T2. And when you calculate that, the answer is 473. And you get to have 3 significant figures. All right, let's look at this one. There's a pressure and there's a temperature. So we have a pressure and a temperature, but our temperature needs to be converted. 25 plus 273 is 298 Kelvin. And we have a new temperature. 50 plus 273 is 323 Kelvin. So we have a first pressure, first temperature, and then a second temperature. So we're looking at P's and T's. So our formula, P1, T1, P2, T2. Okay, so we're looking for the final pressure, P2. If you plug everything in, you get 1.1 atmospheres. So when you plug in volume and pressure, all of the numbers that you have here, you're going to get the number of moles is equal to 0.0354 moles. Be careful because it asks for the moles of gas, but then it also asks for the molar mass. So molar mass is in grams per mole. They give you grams, 0.500 grams, and you calculated moles. And so you're going to get 14.1 grams per mole, which sounds a lot like nitrogen.